Hello, my name is John Moyer, and I want to welcome you to the NIH Office of Disease Prevention's Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions to promote the use of the best available methods and to support the development of better methods. Before we begin, I have some housekeeping items. You can submit questions during the webinar by clicking on the question mark in the WebEx toolbar. Please direct your questions to all panelists. We will open the floor to questions that have been submitted via WebEx at the conclusion of today's talk. The slides and video recording will be posted on our website, prevention.nih.gov/mindthegap, in approximately 2 weeks. You will receive an email when they are available. Lastly, we would appreciate your feedback about today's webinar. Upon closing the WebEx meeting, you will be prompted to complete an evaluation. We would appreciate your feedback as it will help us improve this webinar series. At this time, I'd like to introduce Dr. David M. Murray, Associate Director for Prevention and Director of the Office of Disease Prevention.
Thank you, John. Today's speaker is Jessica Kasza, an Associate Professor of Biostatistics in the School of Public Health and Preventive Medicine at Monash University in Melbourne, Australia. There, Dr. Kasza leads the development of statistical methodology for longitudinal cluster randomized trials, including the step wedge and cluster crossover designs, with a current focus on the development of incomplete step wedge designs. She also has interests in the comparison of healthcare providers and in causal inference. In addition, Dr. Kasza is the president of the Statistical Society of Australia, and in that role is keen to ensure that the Australian statistical community is diverse, welcoming, and inclusive. It is my great pleasure to welcome Dr. Kasza.
Thank you so much. Thank you for having me here today to talk to you all about decaying correlation structures. So before I begin, I would first like to acknowledge that I am speaking to you from the lands of the Wurundjeri people of the Kulin Nations. I would like to pay my respects to their elders, past and present, and extend that respect to all First Nations people around the world. So the work that I'm talking about today on decaying correlation structures wasn't done alone. It was done in collaboration with a bunch of brilliant people at Monash and elsewhere. The Cluster at Monash is a group of people who you see here, who are all involved in developing methods for longitudinal cluster randomized trials. So we've got Andrew and Stefan, myself, Reese and Kelsey are our 2 postdocs. We've got Ehsan, who's just started a PhD with us, and we've got Lizzie, who is also doing a PhD in another area, but we're lucky enough that she works with us a bit of time each week. All right, so let's get started. Let's get stuck into this. I'm going to go through a number of questions today, starting off fairly basically, talking about what cluster randomized trials are. Now, I'm sure many of you have an idea of what these are, know a lot about them, but just to make sure we're all starting off on the same page, I'll talk a little bit about cluster randomized trials. Then I'll move to talking about what a decaying correlation is. Then where you can get estimates of this decay. Then we'll move on to thinking about how we can account for a decay when designing a study. And then some work that we've done on working out whether you should in fact include a decay in your analysis. And then finally, we'll talk a little bit about what happens if you omit a decay when you're analyzing data from a study, from a step wedge trial in particular. All right, so let's talk about cluster randomized trials. So in the standard cluster randomized trials, you've got your groups of participants and you assign those to treatments. Instead of randomizing individuals, entire groups of participants are randomized. So this is necessary when you're considering a treatment that's applied at the group level, for example. So such treatments might be, well, a good example of this is a hospital cleaning program. So suppose we've got some new hospital cleaning program and we'd like to determine whether this new method for cleaning the wards within hospitals actually leads to a reduction in hospital-acquired infections among patients. So we're applying a treatment at the entire hospital level, but we're measuring the outcomes at the individual level. So we can't randomize individual patients to different hospitals. We instead need to randomize the entire hospital. So in this setting, we would randomize entire hospitals to implement the usual cleaning method or implement this new fancy cleaning method. So the clusters that we're considering, well, they could be hospitals. I already mentioned an example there. They could be intensive care units, schools, neighbourhoods, families, any grouping of people or participants. And the intracluster correlation, or the ICC, I'll use the Greek letter rho to denote this. This describes the similarity of outcomes from participants who are in the same cluster. So this rho is going to vary between 0 and 1. So it's restricted to varying between 0 and 1. If rho is equal to 0, it means we've got complete independence between our observations in the same cluster. If it's equal to 1, we've got complete dependence between our observations in the same cluster. And of course, we expect it to lie somewhere in the middle. However, even with really small values of rho, we can still have much larger sample sizes than we may be able to have access to. So this rho describes this similarity of outcomes from participants in the same cluster, and it leads to an inflation in our required sample sizes because of this dependence. So cluster randomized trials aren't always feasible for this very reason. You may do your sample size calculation accounting for this similarity of participants in clusters, and you may find that more clusters are required than you actually have available. So in this setting, longitudinal cluster randomized trials can be a big help. They can turn an infeasible study into one that is actually feasible. In longitudinal cluster randomized trials, clusters are followed over time and measured repeatedly. The participants within those clusters, well, they may be measured only once. They may just pop up in one period and never be seen again, or they may contribute measurements in multiple study periods. So the point is that the clusters themselves are followed over time and are contributing measurements for a duration of time. In these designs, clusters might switch between the control and the intervention conditions. And it's this switching that leads to these increases in power. It's this switching that turns the infeasible into feasible. It's a really useful thing to do. With this switching, we get comparisons not only between our clusters, but also within our clusters. And it's these within cluster comparisons that lead to these increases in power that we see with longitudinal cluster randomized trials. So a good example of a longitudinal cluster randomized trial is the cluster randomized crossover trial. So in this design, clusters are randomized not to implement just the interventional control, but to implement a sequence of treatments. So here, those clusters that are randomized to sequence 1 would first implement the intervention before switching over to the control condition, while those clusters randomized to sequence 2 will then start off with the control but switch over to the intervention. So each of these clusters switches. This means that we now get to estimate the treatment effect using between cluster comparisons and also within cluster comparisons. And it's those within cluster comparisons that are so useful, that lead to these gains in power. However, we now need to think a little bit more about the intracluster correlation. So suppose we've got 2 participants from the same cluster, these 2 smiley people here. These 2 people could provide measurements in the same period of the study, or they could provide measurements in different periods of the study. Do we expect that the intracluster correlation is going to be the same for both of these pairs of participants? We may not. We may expect that those participants who are measured closer together in time in the same period are more highly correlated, or have outcomes that are more highly correlated than participants who are measured further apart in time. So we may not expect that the intracluster correlation is going to be the same for both pairs of participants. I'm now going to move to the stepped wedge cluster randomized trial design. I think stepped wedge designs are really quite wonderful designs. I think they're really interesting from a statistical perspective, but they're also really useful when you can't have this switch back and forth between treatments as you can have for the cluster randomized crossover trial. So in the stepped wedge design, clusters are again randomized to one of a number of sequences of treatment. All of the clusters start out implementing the control condition and then switch over as time progresses to implementing the intervention. In the final period of the design, all of the clusters are implementing the intervention. So what I have here is just one example of a stepped wedge design. You could have more periods, you could have more sequences. You can have multiple clusters assigned to these sequences too. So stepped wedges are useful because all of the clusters know that they will receive the intervention eventually. That may help with recruitment, may not, but it might. They're also really useful when you're considering interventions that can't be undone. So interventions like education or training programs. So suppose you're training general practitioners to help patients deal with their knee osteoarthritis, for example. In that setting, you can't take away training that you've given someone. You can't uneducate people. That's not very easy to do. So we're sometimes dealing with these interventions that can't be undone, in which settings the stepped wedge design becomes really useful. Or if you're considering interventions that are going to be rolled out anyway, so interventions that are being promulgated throughout an entire system, you could use a stepped wedge design to assess the impact of those interventions. But now we're following clusters up over time, perhaps over an extended duration of time. We need to think even more about the intracluster correlation. So once again, let's consider two participants from the same cluster. They could provide measurements in the same period, or they could provide measurements in different periods. But there are a number of different pairs of periods that they could be providing measurements in. Do we expect that the correlations between all of these pairs of participants is going to be the same? Could there be some decay over time in these correlations? So perhaps those participants who are measured in adjacent periods are more highly correlated than those who are measured one period apart or 2 periods apart, for example. So this is where we get to this idea of a decaying correlation. What is a decaying correlation? Well, in order to answer that, we'll consider a model for continuous outcomes. So here we've got our continuous outcome. We've got some period effect. So a period effect is necessary to include when you're analysing a stepped wedge trial because, well, as time progresses, more and more of the clusters will be implementing the intervention. So we've got this confounding between time and treatment. So a period effect needs to be included. We've got our treatment effect. That's what we're most interested in estimating. That's why we do this entire study. We've got our usual statistical random error here, but we've also got these random effects here. And it's the random effects that encode the similarity of participants from the same cluster. And the intracluster correlations, as I've already mentioned, describe this similarity. But now that we're considering intracluster correlations and pairs of participants that are appearing in our study at different points in time, we now no longer consider a single intracluster correlation. We consider an entire within-cluster correlation structure. So this is the collection of intracluster correlations for a cluster that describes the correlation between each pair of participants within a cluster. We can make a whole bunch of different assumptions about these random effects. The different assumptions that we make about these random effects imply different within-cluster correlation structures. So let's look at some models and see what they imply about these within-cluster correlation structures. So this slide is the slide with the most maths on it. I will show you all of these models, but then I'm going to talk a little bit more about what these imply for these within-cluster correlation structures with some examples. So here we've got model 1. So here we've got our outcomes for individual I in period T in cluster K. We've got our period effect, beta T. We've got our treatment effect, theta, and our treatment indicator, XKT. So this will be equal to 1 if cluster K in period T is implementing the intervention and 0 otherwise. We've got our usual error here, assumed to be normally distributed. And then we've got our cluster random effects here, also assumed to be normally distributed. So this model in the stepped wedge literature is often referred to as the Hussey and Hughes model. So that's model 1. I'll talk about what it says about correlations in a moment. Model 2, well, I mean, the name kind of gives it away. It's a constant correlation model. Model 2 is a block exchangeable model. So here we've got exactly the same components, but we've added in an extra term, an extra cluster period random effect. So this cluster period random effect is also assumed to be normally distributed. This block exchangeable model tells us that it implies that correlations for participants in the same cluster in the same period are going to be larger than correlations for participants in the same cluster but in different periods. We then move to the discrete time decay model. We're finally getting to this decaying correlation structure. So in this model, we've got these cluster period random effect terms, and we assume that we've got some form of dependence between these random effects coming from a particular cluster. We assume that they're correlated in some way. And the correlation structure that we assume looks like this. We've got these terms that depend on the distance in time between measurements. So this R value here is going to be a number that's between 0 and 1, usually closer to 1. So what do these three models actually say about correlation? Well, let's consider a really simple example. So suppose we've got a cluster, one cluster observed over 4 periods with 2 participants in each of these periods. We can consider 2 types of intracluster correlation. We've got our within period intracluster correlation, so that would describe what's going on for these pairs that are within a period, so 1 and 2, 3 and 4, and so on. And then we've got our between period intracluster correlation. So this is the correlation between a pair of participants in different periods. So we could be looking at what's going on between participant 1 in period 1 and then participant 3 who appears in period 2, or between participant 1 and participant 5, for example, 2 and 8. It's the correlation between a pair of participants in different periods. So in what follows, I'm going to consider the correlation between participant 1 and each of these other participants in this cluster. So this is the first model, the constant correlation model, the Hussey and Hughes model. So here we've got our individuals in cluster K, we've got our periods here, and we've got our correlation between participant 1 and everyone else. So of course, the correlation between participant 1 and themselves, their outcome, that's going to be 1. This model implies that the correlation between participant 1 and every other participant is constant. It's just equal to some correlation rho. So the correlation between participant 1 and 2, for example, is the same as between 1 and 8. It doesn't change over time. So this model requires only specifying one correlation parameter. So it certainly is very convenient, but it may not always be a realistic choice. You may instead want to consider the block exchangeable model. So in this model, we've got separate within and between period intracluster correlations. So here, the correlation between participant 1 and 2, since they're in the same period, is going to be larger than the correlation between participant 1 and 4, for example, which is going to be a little bit smaller. So participants in the same period have a higher correlation than participants in different treatment periods. Again, this is a relatively frequently applied assumption. It requires specifying 2 correlations now, the within and between intracluster correlations. But it may, again, not always be realistic. We have this step down in correlation, but then the correlation doesn't depend anymore on the amount of time between measurements. We then move on to the discrete time decay model. So in this model, the correlation between participant outcomes depends on how far apart their periods are. So if we look at participant 1 and participant 2, we've got a correlation of rho. But this decays when we start looking at the correlations for participants who are measured in more distant treatment periods. So by the time we get to comparing participant 1 and those in period 4, we see we get this rho times r to the power of 3 because they're 3 periods apart now. So the correlation decays the further apart in time participants are measured. So this now displays these different correlation structures. So we've got our within period intracluster correlations here and then our between period intracluster correlations. So for model 1, these two are equal. For model 2, we get a reduction in this in the intracluster correlation when we're comparing things in different periods. And then for model 3, we get this decaying correlation structure. We refer to this R parameter as the cluster autocorrelation. Let's consider an example for this decaying correlation structure. So suppose you have an intracluster correlation of 0.035, and you expect this is going to decay at a rate of about 5% per period. So your cluster autocorrelation is going to be 0.95. Then your correlation between two participants in the same cluster in the same period is going to be 0.035. But you can see how this is going to reduce the further apart in time we're taking our measurements. Okay, that's great. That's what the correlation, the discrete time decay correlation structure is. But where can we get estimates of this decay? How do we know what values of this decay are reasonable? What numbers should we be choosing there? Is that cluster autocorrelation of 0.95 a reasonable choice, or is that, what do we see in practice? Well, if you're planning a study and you want to get some estimates of this decay, well, you could analyze data that you already have. You could fit these models and see what you come up with. Or you could use estimates from previously published studies. Not too many studies have yet used this decaying correlation structure in their analysis. So previously published studies haven't really published estimates of this decay yet. Or you could use the CloudBank repository. So the CloudBank repository is, well, it's the Clustered Outcomes Dataset Bank. So it's a bank of clustered outcome data sets that we've analysed to provide estimates of these correlation parameters. So this work was led by Lizzie Korovar, and what we've done is we've taken these clustered outcome data sets, we've analysed the 44 continuous outcomes that we have in 29 longitudinal cluster data sets and come up with estimates of these parameters to help guide people to use these decaying correlation structures. So we fit these three models that I've already spoken about a lot to each of the data sets. So first, a little bit of information about the cloud bank. So as I said, we have 29 studies in total. We've got 19 parallel with baseline studies, 6 stepped wedges, 4 observational studies there. And you can see that, well, the number of periods in each of these studies does vary a fair bit. The stepped wedge designs perhaps a little bit longer than the parallel with baseline and the observational studies. We've got differing lengths of periods in each of these studies, ranging from, well, a median of 2 months in the stepped wedge design with an interquartile range of 1 to 6 months there. The number of clusters included in these studies also varies a fair bit. There are some quite large observational data sets in the cloud bank. And the cluster period size, so this is the number of measurements in each cluster in each period of the study, that also varies a bit. Okay, so we analysed each of these studies using these 3 different models, these 3 different correlation structures. And these are the estimates that we came up with. So on the left here, you've got the within period intracluster correlations, these rows, for the exchangeable, block exchangeable and discrete time decay model. The exchangeable, this is the constant correlation model. And you can see that, well, we tend to get values that are, I mean, they're always less than about 0.4, which is kind of comforting because the larger this intracluster correlation is, the greater the inflation for your sample size will be. So with the discrete time decay model, we can see that we tend to get values for this within period intracluster correlation of between about 0.025 to 0.08 or so, 0.09. You can see there's a lot of similarity between the 3 different types of correlation structure. Then we can consider this cluster autocorrelation, so this decay parameter. So that was estimated for the block exchangeable model and then also for the discrete time decay model. For the discrete time decay model, you can see that we get values around the median here is about 0.75, with the interquartile range ranging from about 0.2 up to 0.8, I think. Something to note about the discrete time decay model is that it does allow negative estimates. We don't trust these necessarily. We kind of tend to recommend that those are ignored. They don't make a whole lot of sense. But anyway, there are very, very few in the cloud bank that have these negative correlation, cost autocorrelation estimates. But you can see where the bulk of the estimates lie. Okay, so that's great. But how do you actually use this to help you plan your sample size calculations? Well, the first thing you would do is consider the characteristics of your planned study. What's your period length? What's your cluster period size? What's your cluster type? Are you looking at something in primary care? Are you working in low middle income countries or in high income countries, for example? Then you would go to the Cloud Bank website. I've got the link here, and obtain estimates of the correlation parameters that fit with what your planned study looks like. After you've obtained those estimates, you would plug those estimates into your sample size calculator of choice, such as the shiny Cluster app, and I'll talk you through using that app in a few slides. But first to the Cloud Bank. Well, first to the study that I'd like to design. So I want to design a stepped wedge trial that looks like this. We've got a 7-sequence stepped wedge trial, so 8 periods. Each of these is of length 6 months. I've got 20 participants in each of my clusters in each of these periods. I'd like to detect an effect size of 0.2 with 80% power and a two-sided significance level of 0.05. So this last bullet point will come in handy later when we actually do our sample size calculation. But for now, we want a 7-sequence stepped wedge with 20 participants in each cluster period with periods of length 6 months. So if you go to the Cloud Bank website, you'll be presented with something like this. So on the left, you've got a bunch of different tabs. If you click on the Table tab, you'll be able to select the characteristics of the Cloud Bank you'd like to filter the results by. So here we're interested in studies with period lengths that are less than 12 months. We want fewer than 24 participants per cluster period. I don't mind what type of cluster we're considering to get these estimates. Similarly, I'm not too fussed about country income status. I want to consider all of the study designs, and then you can decide how you would like to view the results. So anyway, after you've made your selections, down the bottom here, you'll come up with a results summary. And below that, if you scroll further down, you'll be able to see what the estimates are for each of the studies that are in the Cloud Bank. But for now, we're just interested in this results summary. And we're mostly interested in these estimates for the discrete time decay. So for this model, what are we getting? Well, I've popped those on the next slide here. So for the Cloud Bank, for studies that fit with our requirements, we end up getting within period intracluster correlations that look like this for these studies. So a median of about 0.053 with an interquartile range that looks like this. Our cluster autocorrelation, well, that has a median of about 0.26 with an interquartile range that ranges from 0 up to 0.689. So this 0 estimate is very optimistic. With a cluster autocorrelation of 0, well, that's going to imply that observations within a cluster in different periods are independent of one another, which may be plausible in some settings, but it seems rather optimistic to me. Okay, so that's what we come up with from the Cloud Bank. Those are the estimates that we've obtained from that repository. But how do we actually account for the decay to design our study? Well, I'm going to use the shiny Crt Calculator. So this work was led by Carla Hemming. And what we've done is develop an online calculator to help you plan your longitudinal cluster randomized trial. So this calculator allows you to incorporate these decaying correlation structures. I would always say that it's a good idea to assess the robustness of your study, of your study power to decays in within cluster correlations, no matter whether you really think there might be a decay or not. It's always good to ensure that your study is robust to a range of choices of within cluster correlation and estimates of correlation parameters. Okay, so this is what the shiny Crt calculator looks like. So here we're interested in a stepped wedge trial, so we select that from our trial design options. We've got a cross-sectional sampling structure, so we're assuming that each participant contributes one measurement only. Our correlation structure, well, we're interested in the discrete time decay correlation structure, so we select that. Our plot setup, we want to look at the number of clusters we require versus power, and you can then select the range of number of clusters per sequence there. If you scroll further down, you come up with a bunch of other things that you can input. So the number of sequences, here we've got a 7-sequence design. Our within period ICC, this is what we've obtained from the cloud paint, 0.053. Our within period ICC lower and upper extremes, we can put those in here as well. And then we can set our within cluster autocorrelation. So here I've set that to be 0.258, so the median value here. We're interested in a continuous outcome, and we want to find a mean we want to be able to detect a mean difference of 0.2. So then on the right, you come up with your power plot. So power on the y-axis, number of clusters per arm, per treatment sequence on the x-axis here. And you can mouse over this plot. So if you go into the app, you're able to mouse over the plot and come up with the number of clusters you require and the power that gives you. So anyway, we've done that for the cloud bank. So just reminding you what our study looks like up the top here. And for each combination of within period intracluster correlation and decaying cluster autocorrelation, we come up with the total number of clusters we require here. So we've got a 7-sequence depth wedge design. We're assuming that we've got equal numbers of clusters assigned to each of these 7 sequences. So all of these total numbers of clusters are multiples of 7 here. And you can see that we get a fair range of required numbers of clusters from 14 down here and for these low values up to 35 or 5 clusters per sequence for these larger values of this decay, these cluster autocorrelation and within period ICC. So I suppose what you would do then is you would go to the researchers who you're working with or consider for yourself what numbers here are feasible for your study and then work out how robust your sample size, how robust the number of your study will be to these varying parameters. All right, that's fantastic, but we've kind of skirted around a bit of an issue here. I've kind of assumed that a discrete time decay is the appropriate choice, but how do you know if you should actually be including a decay? How do you know if a decay is a good choice? Should a decaying correlation structure be used? Well, I would say that when you're writing your statistical analysis plan, you should pre-specify your primary analysis, including what your assumed within cluster correlation structure is. And generally speaking, I would always ensure that that matches with what my sample size calculation assumed. But what about for any secondary analyses or the analysis of other data sets that you might have access to? If you consider these other data sets, it really isn't always obvious what the best within cluster correlation structure is. It's very difficult to look at a data set and get an understanding of these higher order characteristics. So the question we asked was whether we can use tools like the EKA and Bayesian information criteria, the AIC and the BIC, to select a within cluster correlation structure. So this work was led by Reese Bowden and Ehsan Rezai. So I am sort of talking about work that they've done. I was certainly a part of it, but they were the ones who led this work. So what we did was conduct a simulation study in order to get a handle on whether the AIC and the BIC are useful for selecting a within cluster correlation structure. So we varied the number of periods that we were considering. We varied the number of clusters we were considering, the number of participants. So this is the number of participants in each cluster in each period. We looked at a range of intra-cluster correlations and then a range of cluster autocorrelations, considering these three models: the exchangeable model, the Housekeeping Items, the constant correlation model, the block exchangeable model, and the discrete time decay model. We simulated each combination. We simulated data sets, each combination of parameters 1,000 times. And we fitted each of the three models to each of these three simulated data sets. And for each of these model fits, we chose the model with the smallest, well, for each of these simulated data sets, we chose the model that had the smallest AIC or BIC. So what are the AIC and the BIC? A quick refresher or reminder here. So we used the definitions that were used by ASREML R. So this is the package that we use to fit these models. So the AIC and the BIC are both combinations of the log likelihood of your model with some penalization for the number of parameters in your model. So T here is the number of covariance parameters, and you can see that the BIC places a greater penalty on greater complexity. So more complex models are penalized more by the BIC than by the AIC. Okay, so that's what we're dealing with. What did we come up with? There is a lot going on this plot, so I'm going to spend a minute or so talking you through what's going on here. So here we're considering data that was generated assuming the exchangeable model. For each of these simulated data sets, simulated for each value of number of observations per cluster period, that's varying down the bottom here. We've got numbers of periods varying at the second level here. We've got numbers of clusters varying at this top level here. So for each of these, we counted the number of times that the AIC selected the exchangeable model in the red, this top line, the discrete time decay model, the green, which appears in the middle most of the time, and then the block exchangeable model, the blue with the triangles that appears at the bottom most of the time. So the number of times that each of these models was selected by the AIC is counted here. We've got the percentage here. So what do we notice here? We notice that, well, we're generating data under the exchangeable model, and it's very comforting that most of the time the exchangeable model is selected by the AIC. So these red squares are the highest here. We select the correct model most of the time, but we don't always. So this plot here, so this top panel here is the plot that you've previously seen, and now I've got two additional panels here. So here we've got our data generated using the block exchangeable model, and down in the bottom panel we've got data generated using the discrete time decay model. So if you look at the block exchangeable panel, you can see that as we move to the right, generally speaking, we are increasing our sample size. So for all of these models, all of these data generation structures, as we get more data, we end up picking the correct model most of the time. So if we look at the bottom panel with the discrete time decay data generation, we find that the AIC does end up picking that discrete time decay model most of the time. Results for the BIC are similar, and in fact you may not have seen much of a change when I just flicked slides there. So the BIC, the only difference is that the BIC tends to pick simpler models more often. And if we look at the results of the AIC versus the BIC head-to-head, that's what we end up seeing here. So here we've got the results for the AIC in these red squares, BIC in these blue circles, just comparing those head-to-head when they pick the correct model. And you can see that for the exchangeable model, for the exchangeable data generation, we end up picking the BIC does a better job of picking that correctly, whereas for these more complex correlation structures, the AIC does a better job, which is kind of as we expect. So the point here is that for increasing amounts of data, the AIC and the BIC are increasingly likely to pick the correct structure, but the BIC is more likely to pick the exchangeable correlation structure. So with all of this, we see that we do have a way to pick correlation structure, but we only really recommend using these as a guide in the supplementary analyses of trial data. We don't know enough about how these work when we're dealing with the primary analysis of data. So we would recommend using these in analysis of supplementary data. Okay, I'm on to my last question. What if you omit a decay when you're analysing a study? What if you just haven't considered that there might be a decaying correlation when you come to the analysis of your trial? So of course, interest is in estimating your treatment effect. And for the continuous models that we've considered, even if you incorrectly omit a decaying correlation, your estimate for your treatment effect is going to be unbiased. So that's good news. But what about your confidence interval? What's that going to look like? Well, your confidence interval width depends on your estimates of the within cluster correlation structure. It depends on the within cluster correlation structure that you've supposed in the model you're fitting. So for models 1 and 2, these constant correlation and block exchangeable models, ANOVA estimators are available. But for model 3, we don't have any such nice, simple theoretical results that we have for models 1 and 2. So the question we ask here is, what happens if you use model 1 or 2, these simpler models without this decay, when you should in fact be using model 3? So in order to answer this, we considered the confidence interval width for each of our models. So V3, so this is the width of the confidence interval under our true decay model. And V1 hat, well, this is our confidence interval when we use model 1 to estimate variance components. So the data are generated under model 3, but we're using model 1, this constant correlation, to estimate our variance components. So we're going to consider the ratio of these two confidence interval widths for a bunch of different types of designs. So we've got stepped wedge designs with from 4 up to 20 periods in length, and a whole range of cluster autocorrelations from 0 up to 1. We've got our ICC of 0.05 for these, and we consider 100 subjects in each cluster in each period. So I'm going to orient you on the plot before I show you any results. On the y-axis, the vertical axis, we've got our number of periods in our study, ranging from 4 down here up to 20 up here. So 5 is marked, but there is also 4 here. Then we've got our decay parameter, our R, from 0 to 1. So for each combination, we get a number. So here we've got what this ratio looks like when our decay parameter is 0, and we've got 4 periods in our study. And we can see that we get 0.24 here, so a number less than 1. What does that mean? Well, let's look at the whole plot. So here we've got our ratios of confidence interval width for all of these periods and all of these decay parameters. And you can see that they're all less than 1. They're all quite a fair bit less than 1. So this indicates that our confidence intervals are going to be too narrow. If we fit model 1, and we should be, so a constant correlation model, but we should be allowing for a decay, our confidence intervals aren't going to be wide enough. What happens if we fit this model 2, this block exchangeable model, instead of this decaying correlation model? So here we get something a bit different going on. So sometimes our confidence intervals are going to be too narrow. We've sometimes got values less than 1, but sometimes our confidence intervals are going to be too wide. It depends on the number of periods we're considering and the decay parameter we're considering. So it's difficult to know. But the point is that the failure to incorporate a decaying within cluster correlation leads to problems. If you use model 1, so this constant correlation model, instead of a decaying correlation model, your confidence intervals are going to be too narrow. Your type 1 error rate is going to be inflated. If you use model 2 instead of model 3, so you've got this difference between within and between period ICCs, but you don't allow for the decay, then your confidence intervals could be too narrow or too wide. And that depends on your study characteristics. Okay. So my final slide, what are some take-home messages from all of this work? Well, over the past few years, we really have come to an enhanced understanding of within-cluster correlation structures for longitudinal cluster randomized trials. We really know a lot more about how we can model these within-cluster correlation structures in a bit more detail, perhaps. So we've got models that allow for correlations to decay over time. We've come up with a repository of estimates of correlation parameters, including for this decaying correlation model. There are sample size calculators that allow for decaying correlations. So I mentioned the shiny Crt calculator, but that's not the only one. There are others out there too. And we've got some ideas now about how to choose the best within cluster correlation structure. So we thought that we could use the AIC and BIC to do this, but it turns out that, well, if we've got enough data, we can. And finally, we've got some understanding of what happens if we ignore decays at the analysis stage. But we're not done yet. There's still a lot more work to be done. Not all outcomes are continuous, of course. Everything I've spoken about here is in the continuous outcome realm. Time isn't really discrete. Here we've treated time as a discrete phenomenon, but time is a continuous phenomenon. It doesn't come in discrete chunks. Not always, anyway. And then finally, something I'm really interested in is working out how we can help researchers to plan the most efficient designs for their settings. How can we ensure that our designs are as efficient as possible, they place as small a burden on participating clusters as possible? So questions, please do ask me now, or if questions come up later, please don't hesitate to get in touch. I'm always keen to hear from people about stepped wedge questions. So thank you very much.
Thank you, Dr. Kasza. That a very, very interesting presentation. We have lots of questions and not nearly enough time, but I'll start throwing a few out. Can you address what might be some of the reasons substantively why the correlation structure might decay? Is it less variability within the cluster, regression of the mean with respect to treatment effects, something else?
Look, that's a really good question, and I think that's something that we're still kind of investigating. Sort of with this cloud bank repository that we have now, we can kind of dig into some of the reasons why we might be seeing decaying correlations in some data sets and not others. I think part of it is due to a decreased similarity in some cases. A decaying correlation may be observed when you've got a decreased similarity in conditions in a cluster over time. So if you've got participants coming into a hospital, for example, over a duration of 2 years, well, things are going to be changing within that hospital over that 2-year time period. Staff will change, processes will change. Things like that could contribute to a decaying correlation.
And in the cohort case, we often see correlations decline over time. So that might be a discrete time decaying correlation structure or something else that allows for that kind of decline.
Absolutely.
Yeah. So this is a hard question. I'll preface it with that. You recommended that investigators choose a correlation structure based on their primary analysis plan. But when the investigators are developing that plan, they often don't have any idea what the correlation structure is going to be. So the question is sort of, what do they do? Is it advantageous either for type 1 error or power to propose something like a decay structure when they don't know what it's going to be? You showed in the last few slides that there can be problems if you use constant or block exchangeable when the data are actually discrete time decay. But what about the reverse? Are there problems if you use discrete time to decay when the data are really, the correlation structure is really constant or block exchangeable?
Yeah, you're not wrong. That is a tough one to answer. Look, I think if you choose a discrete time decay correlation structure, but it turns out that you've got a constant correlation, that's not going to cause you any problems. You might waste a little bit of information on estimating that decay parameter, but it really isn't going to cause you any problems in terms of power, I don't think. So I would recommend that if the choice is between a constant correlation and a decaying correlation, that you go for the decaying correlation because, well, for two reasons. One, that I just mentioned at the analysis stage, you're not going to lose out by doing that. But two, at the planning stage, you've kind of got some, you're kind of guarding yourself against the possibility of a decay later on. So with a decaying correlation structure, your sample sizes will be inflated because you no longer get the same amount of information from those within cluster comparisons. As you're considering observations further apart in time within a same cluster, they will be less similar. So by comparing those, you get less information about the treatment effect. So by assuming a decaying correlation structure at the planning stage, you can kind of ensure that, well, if there is a decay, my power is going to be protected, I suppose. As for whether you should choose between a block exchangeable and a discrete time decay model, look, I think the problem with these two models is they're not nested, so comparisons are a bit more difficult. I'm not too sure what happens if you choose a discrete time decay when a block exchangeable is correct. I think you might lose a little bit out in terms of power there, but there is a way of, I think that's a bit more, I could probably talk about that for quite some time, but I'll leave it there just by saying it's a bit more difficult.
Okay, might be another study to do to compare those with simulation methods of the sort that you described today. If your preliminary sample size calculation results in a number that isn't evenly divisible by the number of steps in your stepped wedge, what do you do? All of the examples that we see in presentations on sample size calculation assume the same number in each row, but what if the calculation comes up with a number that isn't evenly divisible? Do you add some to make it balanced, or do you go ahead with an unbalanced scheme?
Look, I think you can go ahead with an unbalanced scheme. One thing to bear in mind, though, is that with the stepped wedge design, these different treatment sequences contain differing amounts of information about the treatment effect. If you randomize more clusters to the outer edges of the design, that will result in a more powerful design than if you've got more clusters in the inner sequences of the design. So this is something that we've talked about in a biometrics paper. So look, I think this is a question I get asked all the time too. Like, people do assume that you need an equal number of clusters per treatment sequence, but you don't. You just need to be mindful about where you're randomizing those additional clusters to, and think about the impacts on power if, for example, that cluster drops out. If you've got a bunch of clusters assigned to these outer edges and they all end up dropping out, that's going to have a larger impact on power than if you've got clusters randomized to the inner bits of the stepped wedge design and they drop out.
Thank you. How does the decaying correlation model differ from an autoregressive structure?
It doesn't. It is an autoregressive structure on these cluster period level random effects. Exactly.
Then that's an easy question to answer. What are the general implications of assuming a decaying correlation structure for the sample size calculation that you're going to do when you're designing a cluster randomized trial? I think you almost answered this earlier. I think the answer is going to be, well, you need a larger study if you assume a decaying correlation structure compared to something simpler.
Yes, that is exactly correct. And I'll just reiterate the reason for that. It's because you no longer have the same amount of information from these within cluster comparisons as you otherwise would have. The similarity between these outcomes as you move further apart in time within the same cluster reduces with the decaying correlation structure.
We have another question related to cohort design. So your examples were cross-sectional, one observation per person. What about cohort designs? Are the same points that you've made generally applicable to cohort designs where you have repeated observations on the same people?
Yes. So these observations that I've spoken about here are all directly applicable to closed cohort designs where each individual contributes in all of the study periods. If you're assuming a constant within participant correlation structure, if you're assuming a decaying correlation structure within your participants, then I think you probably need to amp up some of what I've said about the decaying correlation structure at the cluster level. But generally speaking, things do carry over to the closed cohort setting. When you're talking about open cohorts, though, where participants may pop up for a few periods and then disappear and be replaced by someone else who comes along, those correlations, depending on the sampling structure there, depending on how people are moving through a cluster, how they're appearing in this open cohort setting, you will once again get exactly the same results that I've mentioned. But if you've got something a little bit more complex in terms of the open cohort sampling schemes, then I think this would require a bit more thought. I haven't thought too much about that for those perhaps more complex open cohort sampling schemes. It's a great question.
The next question, I think, anticipated the second bullet in your section. There is more work to be done. Someone is asking about, what about continuous time? Is that something that's been dealt with, or is that something you're working on?
So I actually prepared a few backup slides for this, so I might just flip to those. So we've assumed distinct treatment periods, as I mentioned, but time, as I said, is continuous. So something that Kelsey Grantham did during her PhD was assume that you've got clusters arriving at participants arriving at each cluster in a constant rate over time, as I've shown there, and considered a continuous time decay model. So a smoothly decaying correlation where the correlation between pairs of observations depends not on the treatment period of participants, but on when they arrive in the cluster or when their measurements are taken in the cluster. So I've got sort of a schematic of that up here, but I can show you also the continuous time decay model down here. So the problem with the continuous time decay model is that with the discrete time decay model and these other models, you can collapse down to cluster period means and not lose any information at all. That's you've got a sufficient statistic for your treatment effect there. But with the continuous time decay model, you no longer get this collapsing. You can't do that anymore. So it makes dealing with these models a little bit trickier. So we've done some work on that. Richard Hooper in the UK is also a keen advocate of continuous time decay and thinking about time as continuous as well. So I'd recommend reading some of his stuff as well on that.
And we do. Can you tell us a little bit about some of your current projects that involve clustered data?
Oh, well, I could spend a whole hour, but I'll take a couple of minutes. So at the moment, I'm really interested in incomplete stepped wedge designs. So some of the previous work that I've done with collaborators has shown that not all of the cluster periods in a stepped wedge design contribute the same amount of information about the treatment effect. So this indicates that we may be able to come up with designs, incomplete stepped wedge designs, where not all of the clusters are required to contribute data in all of the periods of the study. So something Kelsey is doing in her postdoc with me is look at what happens when we consider a staircase design. So just considering in a stepped wedge, those periods near the time of the treatment switch. And something Ehsan is doing in his PhD work is looking at how we can go from a complete design and sort of poke holes in it and come up with another incomplete design. What does that design look like if we try and do that in an efficient way? So that's something I'm very interested in right now.
So those are fun ideas, and we'll look forward to seeing the publications that come out of that work. We have reached the 5 o'clock point almost, and so we need to wrap up. I want to thank you very much for your presentation. It's been terrific, and there are many questions that we have not gotten to, so we're going to send those to you and hope that you'll work with us and develop brief answers that we can post on our website. I will turn things back over to John Moyer to close us out.
Thank you, Dr. Murray, and thank you to everyone who participated in today's webinar. On the Mind the Gap website, prevention.nih.gov/mindthegap, you will find several resources for this talk, including the slides and a list of references. We will also be posting a recording of today's webinar on our website in the next 2 weeks. You will receive an email with a link to the recording when it's available. Thank you and have a great rest of your day.